In this video, we will see dry run of the code. Now let's do a quick dry run of this problem. Okay. So here is valid binary search tree. Okay. In this, I am returning C check valid with the root and infinity and minus infinity and plus infinity. So let's consider that this is my root. Okay. And I am having these as a value of minimum and maximum. Okay. So let's see. I will first call my function that is CV. So let's call check valid, basically CV. I will write CV with the plus mine with the root. So let me write 3 because 3 is a root, right? Basically this complete 3, and I have a plus infinity, sorry, minus infinity and plus infinity. So minus infinity and plus infinity. This function I will call, right? So it will call first this function, right? I am at here. I will check, is my root is equals to null? No, it's not. Is my root dot well is less than equals to minimum? So what is minimum? That is minus infinity. Yes, it is less than. It is less than. First of all, minus infinity, it is not less than. No, it is not less than your minimum. Basically, it is greater than your minimum. Minus infinity is greater, right? And root dot well, is it greater than equals to your maximum? So what is maximum? Plus infinity. So that is also a false case. No, it's not greater. Okay, it is lesser than your plus infinity. So I won't return false because this condition is not met, right? My root dot well is greater than minimum, right? Minus infinity is greater 3, right? I will put minus infinity and plus infinity here, right? It is greater than minus infinity and it is lesser than plus infinity. So I will call this function root dot left with minimum. So minimum will be same, but maximum will be root dot well. So my next function call will be the root dot left, that is 1, right? And now I am moving in this side. So basically for 1, the maximum point can be 3. So it will become 3, your maximum point, and minimum will be same minimum. So that's why the root dot value I have written root dot well 3, and it will be minus infinity, right? So I will call this function first. Now let's call this function. Is your root is equals to null? No, it's not. Is your root dot well is lesser than minimum? What is minimum? Minus infinity. No, 1 is not lesser than minus infinity. Is root dot well is greater than your maximum? Is 1 is greater than 3? No, it's not. So again I will come to this and I will call this function root dot left. So root dot left, that is null, right? So I will call CV with a null value, right? And basically what will the minimum and maximum? Minimum will be the same as minimum, that is minus infinity, and the maximum will be 1, right? And I will execute now this function, null function, right? CV, basically with null root. And I will come to here, right? And I will check, is root is null? Yes. So I will return true here, right? So when I'm returning true, right? When I'm returning true, I will be at here, right? So basically, can I say my CV of null is done, right? Null root is done, right? So I will call this function. Now check valid root dot right. What is root dot right? Again null, right? So CV here, that is again null, but your root dot well will be 1, basically, and it will go till max. And what is max here? That is 3, right? Again I will check, is your root is null? Yes, it is null. So again return true. So here also I will return true. So now both the conditions are true, right? True and true. So can I say that the final result will be true here? Yes. So from 1 it will return true, right? So if I remove all this thing, so here basically 3 called 1, 1 called these root left, root dot left and root dot left, right? Both return true, right? And now 1 will also return true to 3, right? So can I say 3 called 2 functions, right? The first call is giving, it's returning true, right? Now 3 will call the next one, right? And because this null is done, right? Can I say it will remove, and 1 is also done because 1 is returning true. So that is also done, right? Now I am calling this function, right? And what is this function? CV with the root dot right. So what is root dot right? That is 5. And what will be the minimum and maximum? So minimum will be root dot well. So it cannot, sorry, it cannot be lesser than 3, right? It should be greater than 3, and the maximum can be infinite. Okay. So the range for here, that is greater than 3 and but lesser than the plus infinity. So I call this function. Now first I will execute this function, right? So is the root is equals to null? No, it's not. Is root dot val is lesser than the minimum? Is 5 lesser than 3? No. Is root dot val is greater than maximum? Is 5 is greater than infinity? No. So again one function call, again I will call this function, right? So I'm removing this true and again I'm calling this function. So the calling function is calling of left call, right? So I will call this function CV with a for root, and what will be the minimum? So minimum will be the same. So here the minimum is 3. So the 4 should be greater than 3 and the maximum should be root dot val. So it should be between 3 to 5, right? So yes, I am here in 4. I will first execute this one. Is root is null? No. Is root dot val is lesser than minimum? So what is the value? It's 3 to 5. Is it is lesser than 3? No. It is great. Is it greater than 5? No. Right. So again, I will come here and again one function call. So it will basically again call this null function. I'm not writing complete. I am simply writing CV of null because it will return true. Because I will execute first this function root null. It will return true. So it will return true. Then it will call the next function check valid root dot write. So here it will also null. It will also return true. Right. So both will be true and then it will return true. So can I say CV of null is also done, right? And CV of 4, 3, 5, that is also done because 4 is returning true. So that is also done, right? Now what I will do, I will come here to 5, right? And I will call the right one. So this is giving me true, right? To 5. And I am checking for this one. So I will call this function. See, CV of 5, 3 to infinity is still not completed yet. So I will call this one with a root value of 6 and the range will be greater than 5. Okay, greater than 5. So from 3 to infinity, it will become from 5 to infinity, right? But lesser than infinity. So it will be from 5 to infinity. Infinity. Okay. So again, for 6, right? I will check is root is null. No, it's not. Is root dot value is lesser than minimum? No, it's not lesser than 5. Okay. Is it greater than maximum? No, it's not greater than infinity. Again calling the function. So I will again call it, right? Null. It will return true, right? And again, I will call the right one, then it will also null, it will also return true. So both are return true. So can I say my 6 function is done, right? It called the 2 functions left and right and both are returning true. So yes, CV of 6 is done, right? It will return true. And now you can see, right? Here we have true, here we have true, and condition both are true. So 5 is also done. 5 is getting true from here and true from here, right? From left and right. So yes, it will also return true. So that is done. CV of 5 comma 3 infinity, that is also done. It will return true to 3 and 3 is also done, right? It is getting true from on the left side and from the right side. So this is also written true. This is also written true. So this function complete will return true. So yes, that is done. And here the value will be true. And I will simply say true. Right? Yes, that's a valid binary search tree. Suppose if any of the case is false, basically it will return false. Suppose instead of 4, it is suppose 5. Same thing, right? So that is also one false case. So basically in when once you reach this point, right, it will return false here, right? Let me use yellow pen. It will return false here. Now you are getting one false case, right, and one true case from here, suppose, right? True case, but we have an and condition. That means both should be true. That's why we are using and, not or, because I want to check both the left and both the right should return true, and that's why we are returning in the and condition, right? So this will be my basically now the problem approach for the problem of valid binary search tree. So what will the time complexity of this approach? Basically, I am traversing to each node only once, so the time complexity will be big O of n. What will be the space complexity of this approach? So space complexity of this approach will be the longest length of the your basically your branch. So you can say this is the longest function calling you are doing done. So in recursion stack, basically it will be a stack memory space. So in stack memory, the longest path will be your space complexity. So the longest path is also known as height of the binary tree. So it will be big O of H, right? So time complexity big O of N, space complexity will be big O of H, and that's the dry run of this problem. So yeah, that's all about one valid binary search tree. Okay. In the next video, we will see more problems on binary search trees. Okay. That's all for this today. Thank you.